So what does it really take to send a flawless piece of information from one side of the planet to the other? Well, it's basically an engineer's ultimate quest. It's a journey where you're battling physics, taming probability, and relying on some seriously brilliant design. And today, we're going to map out that whole journey.
All right, take a look at this. This diagram is going to be our map for this entire quest. Over on the far left, you've got an idea, a message, what's labeled here as MT. And way over on the far right, you've got the destination. But everything in between, that's the battlefield. It's a whole series of processes and a channel that's just filled with interference. And the one single mission for any communications engineer is to get that message across the battlefield perfectly intact. So let's really define what our mission is. We're not just sending data. No. We are fighting against physical laws and random chaos to deliver a message with perfect clarity. And honestly, that is the core challenge and really the thrill of digital communications.
You know, every single communication system, I don't care if it's a simple text message or a probe in deep space, it has these three key players. First, you've got the transmitter. Its job is to package the message up for the journey. Then you have the channel, which is the path it takes. That could be airwaves, a fiber optic cable, or even the vacuum of space. And finally, the receiver's job is to catch whatever arrives and somehow perfectly reconstruct that original thought.
But here's the thing. Our signal is never alone on its journey. It has a constant enemy, a villain in our story, noise. You see it on our map there as N of T. It's just this random, unpredictable energy that gets in and corrupts the signal. It's the static you hear on a radio, the glitch in a video call. It's the force of chaos that's trying to flip a binary 1 into a 0.
So with an enemy like noise, how do we measure success? How do we know if we've won? Well, we use one critical metric, the bit error rate, or BER. Think of it as the final score. It tells us exactly what percentage of our bits got corrupted by noise. And the real goal for any engineer isn't just about speed. It's about designing a system that gets this number as close to 0 as humanly possible.
Okay, so we know the mission now. But what about the cargo we're trying to send? We keep using this word information, but to an engineer, what is it really? Well, the answer is actually way more profound than you might think.
The father of information theory, Claude Shannon, gave us this beautiful and honestly really intuitive idea. Think about it. A message like, "The sun will rise tomorrow," that has almost zero information because, well, we totally expect it. But a message like, "A supernova was just detected," that carries a massive amount of information because it's so incredibly surprising.
So what this means, mathematically speaking, is that information is basically the opposite of probability. The less likely something is to happen, the more surprise it contains, and therefore the more information it carries. And the unit we use to measure all this surprise, that's the bit. Now, if we zoom out and look at the average amount of surprise that a source can produce, we get to a concept called entropy. It's the fundamental way we measure uncertainty. A source with high entropy is super unpredictable, which means that, on average, every message it sends is just packed with information.
And here is the crucial insight, the thing to really remember. A system's entropy is at its absolute maximum, when it is the most unpredictable. This isn't just some abstract theory, it's a fundamental law of information, and you can see it perfectly in this next graph.
This graph shows that principle in action. Just look at the very peak of the curve. It happens right when the probability of a symbol is 0.5. You know what that is? A perfect coin flip. It's the moment of maximum uncertainty, because we have absolutely no idea what's coming next, a 0 or a 1. But as you move to either side, when one outcome gets more and more likely, our certainty grows, and the average information, the entropy, just plummets.
Okay, so we've defined our precious cargo, information. But that information doesn't just exist in a vacuum, right? It has to cross the physical battlefield, the channel. So how in the world do we choose the right path for it to travel?
See, the channel isn't just one single road. It's this vast spectrum of frequency highways, and engineers have to choose the right one for the mission. If you need to broadcast AM radio over a huge area, you're going to use medium frequencies. Need the super high data speeds for your 5G phone? You'll be using ultra high frequencies. And for a satellite link to pierce through the atmosphere, that requires super high frequencies. And this slide right here shows the fundamental physics behind those choices. On the left, you can see how lower frequencies actually bounce off the Earth's ionosphere, which lets them travel way over the horizon. But on the right, higher frequencies, like the ones for your phone and your Wi-Fi, they travel in a straight line. If they can't see the receiver, they can't connect. This one physical reality dictates pretty much everything about how we design these networks.
This all leads us to a crucial concept. Every single channel has a fundamental speed limit. It's called channel capacity. It's a hard limit dictated by physics on the maximum rate you can send data flawlessly. And it's all determined by just two key things: the channel's bandwidth and how much stronger your signal is compared to all that background noise.
So, this brings us to the engineer's triumph. Knowing the mission, the cargo, the enemy, and the absolute limits of the battlefield, how do we actually design a system that wins?
Well, the answer is by mastering the art of the trade-off. Because you can't have everything. It's this constant balancing act between performance, efficiency, bandwidth, power, and of course, cost. Think about designing a system for a Mars rover. Power is infinitely precious. You would gladly sacrifice speed to guarantee that every single bit arrives perfectly, no matter how ridiculously complex the system has to be. That, right there, is the genius of engineering. So what's the ultimate weapon in this fight against noise? It's not just about shouting louder with more power. It's about being smarter. Engineers use these sophisticated things called error correction codes, adding clever, redundant bits to the data to create a kind of digital armor. And this armor is so robust that it lets the receiver not just detect that an error happened, but in many cases, to actually fix it on the spot and recover the original perfect message. It's incredible.
And please, don't mistake these for some abstract theories. This balancing act and the magic of error correction are the silent engines powering our entire world. That 5G signal on your phone, your Wi-Fi at home, the GPS that guides your car, even those unbelievable images we get from deep space missions, they are all possible simply because engineers have mastered these fundamental principles. So, we've journeyed from a simple signal all the way to the complex art of engineering trade-offs. We've seen that information is really just surprise, and that we can build a kind of digital armor to protect it. The principles are set, the rules of the game are known, so the only question left is, how are you going to use them to design whatever comes next?